A star died, and for the first time in history, we watched it happen in real time. Not a reconstruction, not a simulation, live data, captured just 26 hours after the star's core collapsed. And what scientists saw broke the standard model of how stars explode. Welcome to Hidden Lab. Today, we're looking at a dying red supergiant, a shockwave caught in the act, and polarization patterns that no existing theory predicted. April 10th, 2024. A massive red supergiant star in the galaxy NGC 3621, about 22 million light-years away, quietly ran out of fuel. Inside the star, the iron core collapsed under its own gravity. The outer layers rushed inward, then slammed into a newborn neutron star. That violent rebound launched a shockwave outward through the star, the birth of a Type II supernova. But the real breakthrough came the next day, April 11th, 2024. The explosion was detected by ATLAS, the Asteroid Terrestrial Impact Last Alert System. Within hours, astronomer Yi Yang at Tsinghua University sent an emergency observation request to the European Southern Observatory. The request was approved immediately, and just 26 hours after discovery, the Very Large Telescope in Chile was already pointed at the dying star. That speed changed everything, because for just a few hours, scientists could see something never clearly observed before: the moment when the explosion's shockwave burst through the surface of the star. A window that usually lasts less than a day. The key tool was something called spectropolarimetry. In a perfectly spherical explosion, light waves cancel each other's polarization. The result? Zero polarization. But if the explosion is asymmetrical, the polarization signal appears. And the signal was not zero. Researchers discovered something unexpected. The first blast of the supernova SN 2024 GGI was not spherical. Instead, it formed an olive-shaped structure around the star, an elongated ellipsoid with a clear axis of symmetry. And that single detail challenged one of the most widely accepted models of how massive stars explode. The standard explanation is called the delayed neutrino mechanism. According to this model, neutrinos heat the stalled shockwave randomly. The result should be a chaotic explosion with no clean axis. But SN 2024 GGI didn't look chaotic. It looked organized, structured, symmetrical. So scientists began considering another possibility: the jet-driven explosion model. In this scenario, powerful jets of matter shoot out from the collapsing core along the star's rotation axis. These jets punch through the star and shape the explosion into an axial structure, exactly like what was observed. Another possibility is something called magneto-rotational instability. Here, an extremely powerful magnetic field forms inside the collapsing core. That magnetic field channels matter outward along the rotation axis, again producing the same symmetrical structure. Which raises a new question: was this event special? Or have all massive stars always died this way, and we've simply never observed them early enough to see it? Scientists now want more answers, and the next tool might deliver them. The Vera C. Rubin Observatory in Chile. Once fully operational, it will scan the entire southern sky every 3 nights, looking for supernova explosions the moment they begin. More early detections, more polarization measurements, and more chances to discover whether SN 2024 GGI was the exception or the rule. For the first time in history, scientists observed the true shape of a supernova explosion at its earliest stage, and everything we learn about dying stars from now on will build on this moment. That's Hidden Lab. Real science, real mysteries, no fluff. If this changed how you imagine a dying star, share this video with someone who loves space and science. Subscribe so you don't miss our next deep dive, and tell us in the comments, what hidden mystery in physics, space, or biology should we explore next? The universe keeps breaking its own rules, and here in Hidden Lab, we keep watching.